And so this is a famous paper now detailing the change in the dissolved oxygen concentration. This is plotted in milliliters per liter off the coast of Oregon. So this is Oregon. This line here is the Newport line, so lots of observations there over time. This first panel shows you 1950 to 1999. The second panel adds the green, which goes 2000 to 2005, right? And then this last panel adds in 2006 in particular, right? And so their point was just saying that there's an increased occurrence of hypoxia happening in the Northern California current. And we'll also add from other work like Jay Peterson's and others that the Northern California current system of the entire California current system does experience the most hypoxia of any of the regions within it. And so part of that story is that it's an eastern boundary upwelling current system, right? So that it means that the winds blow from the north and deep water is brought to the surface, and that because the surface waters are moved offshore. And that source water brings with it high carbon dioxide, low pH, low saturation state, low oxygen, high nutrient water to the surface, fueling the high productivity found in the region. And so iconically, we view the California current system as this advective system, that water that's upwelling is bringing with it that hypoxic water. And largely this view has been shaped by a lot of the work that's gone on in the Southern California current system. And so this is Steve Bograd's papers both in 2008 and 2015. This is from 2008. Detailed a shoaling of that hypoxic boundary, right? That it's moving, it's getting shallower in time, and this benefits largely from the long-term data observations they have in the area from Cal Coffee, right? And they've determined down the Southern California current that it is largely advection driven, right? And influenced by stratification changes in the region. And the rates that are reported throughout the California current are about of decline on decadal timescales are about 1 to 2 micromoles per kilogram per year. So the Northern California current, to kind of put it in context, is influenced by the North Pacific current moving water across, which we've heard a little bit about in the talks earlier. And that North Pacific current bifurcates, and some of it joins the Alaskan gyre in the Alaskan current, and then the rest of it comes down and forms the California current. And the oscillation in this is most often referred to as the North Pacific gyre oscillation. And then as the water, there's also a subsurface current that moves up, brings with it equatorial waters up into the region, and that's called the California undercurrent. And so I thought that Matt might talk about this, but he didn't. There's a recent paper led by Takahito showing that the variability in the North Pacific decadal timescales is largely simulated by the CESM. So Matt showed us this in a different way, but what you're looking at here is time on this axis and the index of PDO here, and you're looking at an annual PDO signal here, at the red, and then also the CESM oxygen there. So showing that oxygen variability on the decadal timescales seems to really be following the Pacific decadal oscillation in the large-scale ocean, in the large-scale North Pacific. But and this was also something Matt touched on, but Mercedes Pozo-Boyul and Mano Di Lorenzo have also shown that, that anomalies from the western part of the North Pacific are advected across the North Pacific current on decadal timescales and end up influencing decadal variability of oxygen within the California current system itself. Those anomalies end up being influencing that source water and the oxygen on the shelf. Recently, in 2019, Steve Bograd put out, now this is Southern California current, Southern California current off in the Cal Coffee region, an analysis where he detailed kind of the influence of the different source waters over time. And so what we're looking at here is 1984 through 2018. This is depth on both of these plots. This top plot is Pacific subarctic upper water, he called it, which is mostly from this region up here. It's characterized by low temperature, low salinity, high oxygen water, and then Pacific equatorial water is plotted down here. And these are both in terms of percents. So he did move in his water mass delineations in this paper beyond solely defining them by temperature and salinity. He included nutrients fields as well. But what he found was that the Pacific subarctic upper water is a majority of the water, especially between these two isopycnals, right? But that the Pacific equatorial water has been increasing in its contribution in time, which is consistent with some other work in the region, like Marion Mineville's and others. So we're getting more of the Pacific equatorial water that's lower in oxygen. It's definitely contributing to the decline in oxygen in the region. And so on top of all this, right, we also have ENSO variability going on in the region. And so what Steve's paper recently showed was that during El Nino events, the Pacific equatorial water, this you're looking at here is Pacific equatorial water during El Nino. This is distance from shore, this is depth. So again, this is percentage of Pacific equatorial water, El Nino, La Nina, and the difference. So what you'll notice is that there's more Pacific equatorial water in the region during El Nino events, which is something that you would expect, but it is deeper in the water column. So, the isopycnals of importance for the water that upwells are deeper, the thermocline is deeper as well. And then, the Pacific equatorial water is not as well pronounced, but that water is shallower. And so the depth of those may influence kind of what you end up seeing on the shelf, right? So Turi et al. In 2018 did an analysis of a 10-kilometer resolution GFDL simulation, ESM 2.6. And what she found was that during these ENSO events that you do see higher oxygen during El Nino and lower oxygen at the surface, higher oxygen at depth. And she attributed this mostly to difference in these different ENSO states to the depth of the thermocline and the solubility, not necessarily the presence of different source waters. So it's more about where the water is, not about where it's coming from in this simulation. So the Northern California current differs from the south in several ways. One of those is that it experienced seasonal upwelling, which means that there is a downwelling season, and I'm going to talk about that. It has more freshwater influence, so this is a schematic diagram from Hickey and Banas in 2008, and there's color-coded retention areas, canyons, and different plumes, and you can just see that there's more of those as you move north, right? There's wider shelves, so the isobaths are also here, so you can see that there's not very much shelf, but there's more of it as you move north. And there's more canyons. And it experiences more what they call two-dimensional upwelling, where we don't have as many filaments and jets, and that's in part because of the decreased presence of headlands. Right? So, oh man, I can never pronounce his name. Does anybody know how to say his name? Friction. Right? Yep. Yep. It's a very nice paper. I don't want to butcher his name. Showed that the Northern California current variability was mostly controlled by local forcing rather than remote. And so this is the southern CCS, the central CCS, and the northern CCS. And what you noticed is from this hindcast simulation spanning 1979 through 2013, for these different variables, so I say mostly because sea surface height was still largely influenced by the remote, but the local forcing was more important in determining the variability for all these other variables, right? So as you move north, the local forcing becomes more important than the remote from this work. Scott Dursky also had a nice paper in 2017 where he analyzed Curtis Deutsch's 26-year hindcast simulation of a ROM simulation for the region. And what he found was that the time periods where you had the lowest oxygen source waters coincided with an upwelling index anomaly. So when the upwelling winds were particularly anomalous in combination with the undercurrent index anomaly, both anomalies he worked on within the body of the paper, and I'm not going to go into. But this undercurrent index anomaly was well correlated with the MEI, so another ENSO indicator, right? So as you bring in more source waters from the equatorial region in combination with the upwelling winds, that's what Scott found that was the driver for low oxygen source waters on the slope. But they didn't make that connection to what has going on the shelf. And so the source waters that end up in the region are not on the shelf. So the hypoxic water, this is from a climatology off the coast of Newport from 1998 through 2009. So these are actual observations from the Newport line, right? This is from Steve Pierce et al. In 2012. And the hypoxic boundary is about here. So a little, around 400 meters or so climatologically. But as we've seen, that can move around, right, from year to year from these variabilities. But the water that upwells is not hypoxic, right? What we find is that seasonally, there's a decline in oxygen on the shelf once you're on the shelf that occurs every season, right? every upwelling season. So here's observations these are observations from EH4, a mooring in 32 meters of water, from a paper by Tom Conley in 2010, showing 2005, 2006 that there's a decline over the course. This is time within the upwelling season. This is days in the upwelling season again from Kate Adams in 2013, showing that repeatedly, 3 different years now, Oregon Shelf, you see the seasonal oxygen decline that happens, right? And so the simulation that I'm going to depend on for the rest of the talk is UW's Cascadia model setup, which you can find out more about on Parker McCready's page. Sarah Giddings wrote a paper in 2014 outlining the physical simulation, but it's a 1.5 kilometer resolution with telescopes to 4 kilometers at the boundaries. It includes rivers and tides, has 40 vertical levers, and it benefits I'm going to talk mostly about hindcast forcing today, although we've done it in forecast mode. And so when I say hindcast, it means that the forcing has benefited from data assimilation, so the large-scale boundary conditions and the winds, et cetera. The biogeochemical model was adapted from Neil Banas in 2009 by Kristen Davis and myself. And it's a simple MPZD with 2 different detrital pools and oxygen, as well as DIC and total alkalinity, but I'm not going to talk about that today. What we found is that, so this is what we're looking at here is time on this axis, 2005, 6, and 7. This bottom panel is bottom temperature. This top panel is bottom oxygen with the hypoxic boundary there for reference. I've shaded this seasonal upwelling time period, so the time periods where we experience that upwelling is shaded gray, and repeatedly during that season, we experience that seasonal decline in oxygen, and you'll notice that temperature remains fairly flat during those time intervals, right? Also on here are some skill metrics to compare the red observations that I showed you from Tom Conley's paper from EH4, it's 32 meters of water, to the black, which is the model. So we have a good sense that the model does a good job with the representation of that seasonal decline. Just quickly, I'll show you another site from more recent times. This is 2014, this is 2015. These are both oxygen, now bottom conditions. I want to focus on this one because it's with the first time we had winter data, so data from the winter time period, courtesy of Burke Hales. And so what you'll notice here is that the decline in oxygen begins well before the onset of the spring upwelling season, and it's fairly well captured by the model. Okay, so what we found in terms of the budget analysis was that the respiration was the large driver over the seasonal oxygen decline, which is consistent with the prior observational studies in the region. And that the sort of patchiness of where that respiration was happening is those regions coincided with the areas of persistently low hypoxia. So we've taken this model and we've gone into forecast mode with it. It's a system called JSCOPE, which I'm not going to talk about here much today, but was funded by both NOAA's MAP and ocean acidification programs. And what we found with that model was that for anomaly correlation coefficient that's plotted here, the forecast was able to forecast seasonally bottom oxygen conditions, right? So we have predictability on seasonal timescales that's shown in this plot here. 6 months out into the future, 2 to 4 months out into the future for these particular variables. And we're working with fisheries folks to extend that now into fisheries work. That's published in 2016. So, but why, right? So why is it predictable on seasonal timescales? Where is that coming from? And so one idea is, so ENSO is the timescale and the mechanism that's largely driving the seasonal predictability in seasonal prediction systems. Mike Alexander has a mechanism that he put out in 2002 where equatorial variability during ENSO was translated to the midlatitudes via an atmospheric bridge. And so that translated to more than sea surface temperature, including mixed layer depth, because the winds were largely influenced by this mechanism. And Mike Jaycox in 2017 showed that this, in fact, was in these NMME, in the forecast models, the large-scale forecast models, that this is now the observed versus the modeled wind stress, forecasted wind stress, and that the winds were, in fact, more predictable during ENSO events. This is largely thought of confirmation that our large-scale simulations are actually doing this atmospheric teleconnection, right? I'm going to skip that in the interest of time. So what you're looking at here is the model interannual spatial variability and hypoxic volume, so going from 0 to 100%. And this is, so I'm just focused on the shelf, so shallower than 200 meters. for all these different years that we've simulated. And you can see that there's regions that don't go hypoxic, and there's regions that persistently go hypoxic, and there is variability within that. So trying to understand that variability, I'm going to relate it to the 3 regions that have NDBC buoys in the region so that I can validate my winds from the model to know that the winds are doing the right thing. And so I'm going to box it into these 3 different regions here on the shelf. And when I do that, I found that the hypoxic volume, which is plotted here, is related to the average intensity of the upwelling winds in the winter. So I realized I forgot to mention that atmospheric teleconnection that happens is maximal during the winter months. So, so that atmospheric teleconnection, translates that wind from the equatorial regions to the Pacific Northwest during the winter months. And so my question was, why in those winter months would there be a biogeochemical predictability, right? Would that be coming from? And so we actually found that downwelling, the intensity of the downwelling winds is related to the hypoxic volume on the shelf the following summer, right? So why would that be? It could be that there's stronger mixing, downwelling leads to more ventilation. It could be that the stronger mixing or stronger downwelling winds are associated with conditions that allow nutrients to be maintained over the winter, so a preconditioning. It could also be this transport of poleward flow into the region. So I'm going to eliminate the first one right off the bat because the direction of the trend is opposite to what you would expect if that was the case. So what we're seeing is that with more intense downwelling winds, you have higher hypoxic volume the following summer. So that is the opposite direction to what you would expect for ventilation to be the answer. I'm also going to eliminate this last one as a possibility because we've looked at transport in a bunch of different ways. I'm not going to show you that. I'm happy to talk to you about it later, but it has not related in our simulation years to the hypoxic volume on the shelf. So how would nutrients hang around in precondition? And it turns out that as you have more intense downwelling, we found that you have more average total nitrogen above the mixed layer depth. So it's also positively correlated with the surface nutrients. So as you have more intense downwelling, you actually end up with more nutrients in the region. That includes dissolved and particulate phases in the model. So what I think is happening is that you get this onset of the upwelling season that brings a particular type of source water with it. Respiration draws down oxygen over the course of the upwelling season. And then the fall transition happens and mixes away that organic material and reoxygenates the shelf. And depending on how much mixing you have both from the winds deepening the thermocline as well as the other methods of mixing that the winds like convective and shear-based mixing that would happen over the winter, you could have a deeper thermocline or deeper mixed layer depth, right? Which would have you would have a longer particle length to respire particles as well as the potential to entrain deeper nutrients. Whereas if you had a shallower mixed layer depth, right, you wouldn't have that space, and more particles could essentially escape that mixed layer depth, which would then be re-upwelled the following season. And so the balance of these processes over the winter influence that following summer's oxygen and nutrient content. And just as a side note, there's also been observed an increase in the downwelling winds have intensified over the past several decades by more than one regional study. So to conclude, I'll just say that while respiration and sediment oxygen demand seem to drive that seasonal decline, interannual variability is influenced, if not driven, by preconditioning of the shelf water the winter prior. And that the winter preconditioning provides a local biogeochemical mechanism that amplifies these kind of climate teleconnections. And I think we need to move beyond kind of traditional model evaluation skill assessment activities to evaluate the process skill, which is important to understand and build these forecast systems. And so with that, I'll just acknowledge funding sources and happy to take any questions.
Excellent talk. And I was wondering, you haven't mentioned temperature. Does enhanced downwelling also bring warmer waters to the sediment or the deep waters where respiration could be faster as a result just of
it could.
metabolic
We
effects?
don't have that. If that would be one of those things that we could look to see a process-based evaluation. That sort of feedback does not exist in our simulations the way they are now. Whether or not it should is a question that I think is interesting. Yeah.
Hi, Sam. Nice talk.
Hi,
George Wallbusser, OSU.
Yeah, George.
So I'm just wondering if contact time, like is there a longer residence time? Is that part of what your preconditioning is? So there's longer residence time of the water on the shelf for contact with the sediment and then picking up the respiratory products?
It could totally be that as well. I'm trying to figure out how to diagnose, how much is coming in from entrainment versus the particles, and it's entirely possible that the contact time with the sediments plays a role here as well. Mm-hmm. There's more back there.
Oh, okay. I was curious about some of the variability on shorter timescales. So your talk focused on the longer timescales, but do you have a feeling for what's driving the variability in oxygen dynamics on shorter timescales?
Like subseasonal?
Yeah.
Yeah, no, I think we have a lot of data to sift through to try and figure that out. And part of it is, efficiency of benthic pelagic coupling. I think we'll hear a little bit about sediment oxygen demand in a later session, and so I look forward to learning about that as well. But yeah, no, but we haven't done budgets of shorter term events. I think there's a lot there to look into.
Thanks.
Well, I have a question. In your last slide, you had an interesting comment about the difference between a process skill and a model skill. Was that how I got it? I was wondering if you could elaborate a little bit on how you think about that and how you validate that.
For example, I'm not sure, and I would love to hear that if we have observations to look at the particles in the water column on the slope, in the Northern California current over the winter, and to sort of diagnose whether or not that process is actually going on, interannually in the model, right? I think there's, and so a process of respiration, for example, kind of is that the process of respiration well constrained by the simulation or not? And so how do we constrain that? And then sort of the feedbacks, like what Andres was insinuating about the interaction with the sediments and that interaction with the temperature, those sort of feedbacks mechanisms, are we representing those well in simulations going forward? Mm-hmm. Yeah.
I have a question too.
Yeah.
Are the years with high winter winds also the years with higher precipitation and river flow?
Yes, and so I was concerned that it could be more rivers coming out, but I looked at salinity, and there was not a relationship between while there is a relationship between the surface nutrients in the winter and hypoxic volume, the surface salinity and those surface nutrients was not well correlated. But we have a couple of, so I don't think it's coming from the rivers, even though there has been prior work that suggests that, and observations do show that there are more nutrients that come out in the rivers in the region over the winter. So so I have a simulation where we turn the rivers off, and I'm looking forward to analyzing that in order to fully know the answer to that question. But the correlations do not suggest that that's the case. Yeah. Oh, Claire. Mm-hmm.
Claire Reimers, Oregon State. Could you explain a little more how you determine the hypoxic volume and how well constrained that is by observations? And, it may be that the hypoxic waters are spatially variable, and are we capturing that, do you think?
Yeah, great question. I spend probably the majority of my time thinking about model evaluation and validation rather than the other pieces. But we did look at the time periods where there were bottle samples throughout the water column, and that's in our 2015 paper. Some of those, but those are happen once or twice a season, right? And not over time. And so those sort of the water column sampling that we've compared against, the model that seems to do a good job. But most of the moored observations are solely at the bottom or solely at the surface, right? And they don't capture sort of the variability throughout the whole water column. So yeah, so we've done comparisons against like all the OA center cruises that happen, on the West Coast, as well as some of the WOAC cruises, sort of the regional cruises, and the Newport line observations that span the water column. But the Newport line has the most time, as you know, covered by that.
Great, thank you.
Yep, thank you.